Okay, back for the third and last part of the lecture. I hope that the Hess's Law example was not too confusing. Sometimes it can be. So I definitely suggest you take a look at the video that I posted for it. And if you're still having trouble, check back with me. So I'm going to talk a little bit about how to calculate delta H from standard enthalpy values that will come from a table that you'll find on page 243. This is very simple, very straightforward, really just plug in the numbers and you're good to go. So the delta H for a reaction can be calculated from standard molar enthalpies of formation. That's what that symbol stands for. So when we calculate this, we're going to, the values that are given in the table are for 1 mole of the compound being formed. So if we can determine the change that occurs as reactants go to products, then we can determine the standard enthalpy change for the reaction, which is what our goal is here. So I have this example here, which is not very clear. It just didn't copy off very clear. So I'm going to go to this other example that I have here. So the reaction that I'm going to talk about is methane plus oxygen yielding 2 moles of water and carbon dioxide. And so how we calculate the enthalpy of the reaction is with this very straightforward equation, which is in the brackets, the sum of the standard heats of formation. That's really the symbol that indicates that it's the standard heat of formation, which means that it comes from the table. So the standard sum of the standard heats of formation of the products minus the sum of, that's just a Greek symbol, sum of, it looks a little more like that, sum of the standard heats of formation of the reactants. So once you have your equation that you're working with, here's the model that you would follow, that the delta H, the change in enthalpy, that's what that means, for the reaction above would be, I would take 2 times the value given in the table for water. I would take 1 of the value given for carbon dioxide, and then I would subtract the heat of formation from the table. Again, these values all come from the table. They're standard values, and that's a little naught symbol. That's what that's called. And I would just look those values up on that table that is on page, I can't remember what page I said it was on, page 243. Okay, so you'd reference that page 243 in your textbook to find these values. These are what you would find for this example. And then I just plug them in. It's 2 for every 2 moles. Well, sorry, for 1 mole, it's negative 285.8 kilojoules per 1. But I have 2 moles of water in this balanced equation, so that 2 comes from the 2 coefficient here. It's the only place you'll see a coefficient in this example. Plus the heat of formation, the standard heat of formation of CO2, which I'll look it up, is negative 393.5. And then I subtract, that's the equation, the negative value for the standard heat of formation for methane, which is negative 74.3. And then I'm going to take the heat of formation of oxygen, and you'll note that it's 0. So what you need to know is that elemental substances include anything like a solid metal, any of your any of your gases that exist in the molecular form, oxygen, hydrogen, nitrogen, fluorine, chlorine, anything that's elemental will have a value of 0. And you don't even really need to remember that. If you remember this format, when you go to look up the elementals, you'll see that the values don't exist. They're not listed. The space in the standard table is 0. So then I just perform a little bit of addition and subtraction here, keeping track of my signs, and I get a value of 890.8 kilojoules, and I didn't do a very good job keeping track of my signs. That is actually a negative 890. And that's really important that you keep track of the sign, because it's a huge difference between a positive and negative. The negative means that it is exothermic, energy is released. Okay, and then if it were positive, of course it would be the opposite, which would be the endothermic reaction. Okay, so on to the next page. So the next part of this lecture, so you can ignore the bottom page, the bottom part of that last page. That was kind of hard to read. So the next piece, one of the last pieces, is calculating delta H with bond energies. So what we can find, we call it the bond enthalpy, but the bond enthalpy should be very close to the overall enthalpy of the reaction, because it's the amount of energy needed to break and form bonds, which is really what is actually happening in a chemical reaction. So when a bond is broken, the bond enthalpy is positive, energy is taken in. When the bond is formed, then bond enthalpy is negative, heat is given off. So here's an easy example. How do I calculate this? So again, now there's a different table you would reference, the table for bond enthalpies, and it's on page 247. So in this example here, I'm going to look at what do I have, what's being broken as I decompose H2O gas, all right, H2O vapor, what's being broken. And I have 4 hydrogen-oxygen bonds. So if you look here, I just drew a quick little sketch of 2 water molecules there. And you can see there's 1 hydrogen-oxygen bond, there's another, and there's another. And so it's 4. It's because I have 2 moles of water. So I have 4 plus whatever the bond energy is for a hydrogen-oxygen bond. And then I would do and then I'm going to add to that the value for the bond 2 hydrogen-hydrogen bonds, because here that would really look like this, a hydrogen bonded to a hydrogen, and then another one. And so I need to form both of those bonds. So when I form bonds, the bond energy is negative, opposite of breaking. Breaking bonds adds energy, forming bonds releases. And then I do the same thing, negative bond energy for the oxygen. And there's only one of those bonds, so it's just O2, 1 molecule of it. So now I go to that table on page 247. I look up these values. I'm going to take 4 times the value for the bond energy for an oxygen-hydrogen bond. I'm going to add to it 2 times the negative bond energy for the hydrogen-hydrogen bond, and then I'm going to add to that the negative bond energy for the oxygen-to-oxygen bond. And those are the values that I get when I do my little bit of mathematics there, and I add those values up, and that is the answer for the change in enthalpy for this particular reaction. And then the very last piece here in this chapter is making the connection between Q of a reaction and energy. So we always say that Q is conserved, heat is conserved. So the Q of the system, we said this very early on, is equal to the negative Q of the surroundings. Okay, and so we say the same thing for energy. We usually talk about them interchangeably for simplicity's sake. But there's more to the energy piece than just the heat. So again, that Q is the heat. W, it represents the work. So the amount of energy is really related to both the heat and the work. So the total energy, the total change in energy of a system is equal to the sum of the heat and the work transferred between the system and the surroundings. So energy is all about heat and work. And so you really just need to know how to identify whether work is positive or negative. We know how to tell if heat is positive or negative, but we can say that work is positive when work enters the system from the surroundings. Just like heat entering the system, work entering the system is positive. And when work leaves the system, the W is negative. So it really, what we're looking for is energy released? Typically you want energy released in a particular useful chemical reaction. And so it's important to know, is the energy negative or positive? And the way to do that is to calculate using the Q plus W, knowing these conventions here. Q is positive when heat is absorbed. Q is negative when heat is released. So that's the end of that chapter.